Did everybody get a copy of the notes I printed out over there? I do have some official business. Normally my office hours on Tuesday, Thursday are what's on the syllabus on Tuesday, Thursday is 9 a.m. to 11 a.m. That's what's on our syllabus. Has anybody come to see me in my office? Exactly. Right. Right. Nobody has come to see me. I didn't want to take, yeah, okay. I knew someone had to have come. But I can tell you this, I haven't seen anybody on a regular basis, all right? So this probably won't impact you too much. I'm changing this officially. It's now going to be Tuesday, Thursday, 10 to 11, and then 3 to 4. All right? I'll change it on the syllabus when I remember to go do it. This is upon the request of my calculus class that's after this class. I stay in this room and I teach a calculus class. And I have about 8 students in that class that could do the 3 to 4, so I'm going to change my office hours for those students. So, you know, if that works into your life, then you're welcome to come also. All right, well, 5-1. Polynomial functions. Did I post the solutions to this test? Okay, I will post the solutions. So if you have any questions about the test, you go back, you compare your test to the solutions online, and then, you know, feel free to meet with me. I'm not going to take class time to do individual, like, let's talk about your test. You know, you'll have to come visit with me if you want to do that, all right? So we're going into a new chapter, Chapter 5, called Polynomial Functions, and well, Chapter 5 is, it's probably just called Polynomials. Let me see. Oh, Polynomial and Rational Functions is the chapter. We're in the first section, which is Polynomials. So up to this point, everyone in this class should be comfortable with 2 types of functions, lines and quadratic functions, which are the parabolas. Right, those are the 2 things that we assume now you can graph those if we asked you. We're going to focus the next few weeks on graphing 2 other types of functions, one being polynomial functions, the other being rational functions. And as you're going to see, they get a little involved, all right? Especially the rational functions. They can get kind of nasty. But let's first discuss what a polynomial function is. A polynomial function is the sum or difference, that means plus and minus, right, of terms. Terms are things like 2x, 3x squared, 5y. If you have a number and a letter, that's a term, if they're connected with multiplication. So if you take the sum or difference of terms, but each of these terms is a number times x raised to a positive integer power. Positive integer power. What the hell is a positive integer power? You know what? I should change this. Change this positive to non-negative integer. Now, I change it to non-negative because if I say positive, that means it could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are integers, positive integers. But 0 is an integer also, and you can have a 0 power. You just can't have a negative power. So by changing it to non-negative, I'm saying throw out all the negative integers. 0's okay. All right? So if we have things with numbers and x's raised to non-negative integer powers, then we've got a polynomial. So here are some examples. 3x plus 5. That's a function. How many terms does it have? 2. The first term has a 3, a number, in front of x to a power. What's the power on this x? 1. This is a 5 next to an x to a power? It's x to the power 0 is next to that. Now it's not written, right? But would you agree that 5 is the same as 5 times x to the 0, because x to the 0 is a 1, and 5 times 1 is 5. So that does satisfy that we do have, each term does have a power of x in it. We just don't write it if it's that. Okay, this one, 2 terms, right? This one, what's the number in front of this one? Okay, and then the power on that, 2, that's a positive integer, right? We're good. This one, -4, and then the power on that x, 1. So as long as it's a number and then an x to a power, and that power is not negative, and it's an integer, you've got a polynomial. So here's another one. It's 2 terms, right? Number in front, -1. Power is 3 here. Number is 9. Power, did I say 1? Power is 3. This one, the power is 1. This one, 1, 2, 3, 4 terms, right? Each one of those is a number, x power. Okay, those are examples. What I will kind of stress to you, what type of function is this? It's 2 terms, yes, but what type of function? If I asked you, hey, graph that, it's a line, right? That's a line. That looks like y equals mx plus b. I'll stress that in a second. This one, what type of function is that? Quadratic. Quadratic, right? X squared. So that looks like ax squared plus bx plus c, kind of. All right? So we've actually already studied polynomials. You just didn't know they were called polynomials. But we can now go into more complicated things like this. I like to draw a picture to kind of represent what's happening here. If you look at this big pot of functions, okay, this is a big pot. Inside of it are all the polynomials. I'm just going to put polys. All your polynomial functions are in there. There's a smaller group of functions in here that are your lines, your linear functions, and then there's a smaller group in here, your quadratic. Okay? So every linear function is a polynomial. Every quadratic function is a polynomial. But there are a bunch of other functions out here that are more than these two, if that makes sense. Yes? I should be recording, yes. I'll double check that it's picking up my audio, though. Hello? Yeah, I just looked for that little bar to move. Thank you for reminding me, though. Okay, so now, with every polynomial, we have these 2 things that we want to be able to identify. One of them is called the degree. The other one is called the leading coefficient. All right? So the degree of a polynomial is the highest power of x which appears in the entire thing. That's called the degree. The leading coefficient is the number that was in front of that highest power. Most students have no problem with this concept. So here are some examples. What is the degree of this right here? What's the degree? 1, because the highest power on the x is 1. What's the leading coefficient? 3. What is the degree of this polynomial? 2. What's the leading coefficient? 1, the one that's in front of this, right? What's the degree here? 3, leading coefficient? -1. What's the degree here? I got you. 6, right? 6, leading coefficient? -4. It's the highest power you see in the entire thing, right? So what we always like to do with polynomials is we like to write them in what's called descending order. We like to rearrange them so it's highest power of x down. I didn't do that here on purpose to just make sure that you are, looking through the whole thing first. Make sure you see that highest power, identify it, and then look at the number in front. Now, believe it or not, those 2 pieces of information will help us significantly when it comes to trying to graph these. Okay? It's going to help. This number 4, -4, would be our leading coefficient. So the leading coefficient is determined after you find the one with the highest power. Find that one first. Find that one, the degree, that x term, the number in front of that one. So the leading coefficient is not the number in front in the very beginning, because it has to, you could rearrange it. So identify that highest power, look at the number in front. Okay, so remember from lines, okay, remember we had a line, we said y was equal to mx plus b? Every line is a degree 1 polynomial, isn't it? The degree on this, the power on x is 1. In fact, what's the leading coefficient of a line written in this form? the m, right? That m, whatever the number is in front of the x, that's our leading coefficient. But we didn't. We wrote it a general line. We always wrote mx plus b. Why did we put m? It represented the what's the slope, right? We used the letter m because everyone remembers slope is m, right? And then when we got to parabolas or quadratic functions, I told you there were two forms, but one of them, the expanded form, was this one: y equals ax squared plus bx plus c. Remember that? We said the a, the b, and the c were just some numbers. So this is a degree 2 polynomial. Do you all agree with that? Every parabola is a degree 2 polynomial. What's the leading coefficient of a parabola? The a. All right, so then all of a sudden, remember we had lines, we have parabolas, those belong to polynomials. So now I try and give you a general formula for a polynomial, and it turns into this big, ugly, nasty looking thing, right? And you're like, what the hell? Why do math people have to be so cruel, right? Doesn't that formula look pretty bad? Okay, so I'm going to try and explain why this is, because when I was a student, I was like, why are they doing that? Like, I just don't understand why it has to be so complicated. This didn't seem so complicated to me. Ax squared plus bx plus c. Fine, right? So let's look at this first, and then we'll try and figure out why it is this way. A general form of a degree n polynomial. So if the power on this polynomial is n, which means I'm not going to tell you what it is, right? Then what it's going to look like is a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 plus ... means continue that pattern all the way until you get to a sub 1 x to the 1 a sub 0. What? A sub n minus 1, a sub n minus 2, all the way down to a sub 0. Those are just numbers. So this is a number, a number, a number, a number, and then they're all sitting in front of what? X to a power. X to that power, but one less than it. X to that power, one less than that, right? So that pattern keeps on dropping down. Also, we have that this first number can't be 0. Why can that number right there not be 0? Then this wouldn't be here, right? And then it would not be a degree n polynomial because this whole thing would be gone. Yes? Okay, so my question here was, why is this so ugly? Why is that formula so ugly? So let me try and motivate this by listing out, we had y equals mx plus b, right? Then we had y for parabola was ax squared plus bx plus c, right? So what if I wanted to do a general form of a third degree polynomial? I could do something like this, right? Ax cubed plus bx squared plus cx plus d, right? That's a third degree polynomial. So why not just give you that for a third degree? Because the degree can be n, right? It can be any positive integer. So, all right, what about a fourth degree polynomial? Ax to the fourth plus bx cubed plus cx squared plus dx plus e. That's a general form of a fourth degree, right? Using a, b, c, d, e. What's right? I'm going to run out of letters, aren't I? What if I have a 60 degree polynomial? You cannot give me a general form of a 60 degree polynomial, right? Unless I write it like this. Y equals a sub 60. So that's just some number. I'm using, instead of a, I'm using a sub 60. X to the 60th. Plus, now the next one would be a sub 59. X to the 59th power. Plus a sub 58, x to the 58. And then plus, and I keep doing that, right? And each of these, a sub 60, a sub 59, a sub 58, is just, it's just labeling it, exactly. It's just using something other than a letter to represent the thing in front. And you will never run out of those, right? So it's very common in mathematics to use a subscript like that because we're limited by the 26 letters of the alphabet, right? Okay, I hope that makes sense. All you really need to know, okay, all you need to know is that these are polynomials, okay? These are polynomials. But that's the general form. Now, something else that'll come up in your homework. Let me give you an example of something that would not be a polynomial. Y equals x squared plus 3x. Is that a polynomial so far? Yes. Minus the square root of x. Not anymore. Because the square root of x means x to what power? Anybody remember? 1/2 power. And this is not an integer. 1/2 is a rational number. It's a fraction. And therefore, this is not a polynomial. Now, is it a function? Absolutely. Does it have a graph? Absolutely. Can you graph it in here? No. Take calculus. We can handle that. All right? Another example, y equals x to the 4th plus 1 over x. Is that a polynomial function? Well, isn't 1 over x the same as x to what power? -1, isn't it? Because when you take x to a negative power, that means drop it down. You can drop it down. So I'm going backwards. I'm taking the x that's down here. I'm pushing it up to the x to the numerator, which means I have to change the power on it to a -1. But I can't have a negative, right? So this is the same as x to the 4th plus x to the -1. This is not good. This one up here was not good. Both of these, no, this is not. These are not polynomials. All right. Okay, so what do polynomials look like when you graph them? We already know what a line looks like, right? We already know what a parabola looks like. All polynomials are smooth and continuous. Now, on your notes, it does not have this because it just took up too many pages. It wound up turning into like a 13-page set of notes, and I took this out. Plus, you can't change, like manipulate this. So here's a polynomial. This is a little thing I made a couple of years ago. I can select the degree of the polynomial I want, and I can go up to 6, all right? We're not usually, in this class, we're not going to go past 6-degree polynomials, all right? So let me take a first-degree polynomial. It's a line, right? This thing called a root, which we'll discuss in a little while, that is, I made the root -3. That means at -3, it's crossing through the x-axis. And then this is the actual function right here. Do y'all see it? F of x equals x plus 3. So that's a line. Slope is 1. I can change the slope. And you see how the function changes? Yes? Now I have a steeper slope, but it still passes through at -3. Degree 2 polynomials. Look at this. That should look familiar, right? What I'm wanting you to see right now is the smooth and continuous, what this means. Smooth means as you draw it, it doesn't all of a sudden have like a jagged corner or something, or it doesn't, you don't like pick up your pencil and move to a different spot, right? I can draw this nice and continuously smooth curve. No sharp corners, no jagged edges, yes? The line, well, smooth, is a line smooth? Are you happy with that, a line being smooth? I mean, it's just a straight line, right? Like you rub your hand on it, it's smooth. If it's a parabola, you know, it's still smooth, right? As you move, there's still, right? Imagine trying to rub your hand, where's that marker? You know, across something like this, okay? Like the absolute value function, right? You're going to have like, oh, wait, little jagged corner there, you know? It's not nice and smooth. In this class, we don't really get into what the definition of smooth is. Again, in calculus, you actually have precise definitions of what's smooth, and continuous is an entire section in calculus that you cover. All right, so let's see a third-degree polynomial. Right? See a third degree? There's a third degree. Let me scale this back. There's an example of a third-degree polynomial. Notice in this particular one, it looks like it touches right here, doesn't it? And it looks like crosses through the x-axis here. This is the actual function right here. That's it. Can you all see that? X cubed plus 3x squared. That's what its graph looks like. Smooth and continuous? Yeah? Let's go with the 4th degree polynomial. Let me add some flavor to this thing. Whoa. There. So it like goes down, comes through the x-axis, goes back up, comes down again, then goes back up. There's your 4th degree. Smooth and continuous. 6th degree? Smooth and continuous. All right? Now it just cuts off because the graph stops there, but it goes down here and comes back up. Any questions on smooth and continuous? Okay, end behavior. What is the end behavior of a polynomial? So when we say end behavior, thinking of a graph, the ends, you have the left end of the graph and the right end of the graph, yes? So we have what's called left-hand behavior and right-hand behavior, if you're looking at the graph over there, left and right. So let's talk about no, we'll do right because it's the first one I do. Right-hand behavior would be going in that direction, which is the positive direction, right? To your right. In that direction forever is infinity, isn't it? Infinity is going that way. So what we're saying when we talk about end behavior is as x gets really big and positive, going out the right side, or this is new notation for us, as x with a little arrow to infinity. As x approaches infinity is what that means. Or when x gets really big but negative, so that means to the left. We use this notation, x approaches negative infinity. So with polynomial functions, when you go out to the right forever, or you go out to the left forever, the polynomial behaves like this. What is that? That's your leading coefficient, and that's your degree. It acts like just that one term. It doesn't act like anything else in the polynomial. So no matter what's going on with the polynomial, if you identify that degree term, the highest degree term, and its leading coefficient, the entire polynomial is going to behave, whatever that one does, is what it does out towards the edges. Okay, so I'm going to ask and see if we can figure this out, like interpret what I just said. So I'm giving an example here. Got to wake up, man. Go do some jumping jacks in the hallway. Come back. I won't do sleeping today. If I had a 90 average, we could play thumbs down, heads down, thumbs up today, okay? But we're not going there, all right? You good? Okay. All right, so this, I want to change it a little bit. Let me make this. Okay, so I want you to focus on this right here, 2x minus 6. This is a line, right? Let's talk about what happens as you go out to the right. I mean, you can tell from the graph, can't you? As I go out to the right, where's my graph going? To infinity, positive infinity, right? As I go out to the left, where's my graph going? Negative infinity. Now, let's see if we can make sense out of what this was saying. If you have a polynomial, you want to identify that degree term, which in this case would be what? This 2x, right? That term right there. Whatever 2x does is what this thing does out the right side. So let's try this. If x is huge, what's 2 times a huge number? So I'm going out the right side to a huge number, like take 1 billion. What's 2 times 1 billion? 2 billion. That's big, right? You go out to 20 billion, right? 2 times 20 billion is 40 billion. So what's happening is it's going to positive infinity, yes? And we ignore this. That's what this note is saying. You just ignore everything else. Now, let's go the other direction. So give me a big negative number. Negative 1 billion. 2 times negative 1 billion? Negative 2 billion. It's a big negative number, which means that it's going down this way, yes? Got that? Well, let me give you another example. Let's do a degree 4 polynomial. Throw some stuff in here. Okay, so the way this is written, right? This is a polynomial, everyone agree? Right? So let's talk about the left and right hand behavior. What we do is we focus on first, go find the term that has the highest power, which is this one up front, right? Whatever that does is what this function does on the ends. Whatever that one does. So go out the right side, give me a very big positive number. If I plug it in here, it's going to be huge, right? And then times 2, what's it going to do? Double it, it's going to be big, right? So as I go out to the right, this function should be going up to a very big positive number, yes? So it should be going up on the right. Now what about if I go out to the left? Plug in a big negative number. What happens if I put a big negative number in here? It gives us a positive because it's to the 4th power, isn't it? Anything to the 4th power will return a positive number, right? Negative times negative times negative times negative will give you a positive. And then times 2, still going to give you a positive. So as I move out to the left, I get a very big positive number. That means the right-hand behavior is that it goes up, and the left-hand behavior is it also goes up, as you can see indicated by the graph. Do you see that? Okay, does that make sense, y'all? Okay, now what if I change it? Let me change something here. So I changed the polynomial. This is still a polynomial, right? I go find the highest power term right there. Tell me about the right-hand behavior, going out the right. It's going to go to negative, let's say infinity, because you plug a positive number in there to the 4th power. That gives you positive, but then you multiply by -3, which makes it negative. So it should go down on the right. What if you plug in a negative number? So go out the left side. Negative number to the 4th power, it's positive, but then the negative in front of it drops it down. So now you see the graph, it kind of is hard to see, but this goes down as you go out to the left. I think I can, there we go, there. Yes? Goes down on both sides. Questions? Let's do one more. Fifth degree. How about this one right here? You can see from the graph, just look at the graph right here. What does the left side do? Up, right? Goes to positive infinity. Right side goes down to negative infinity. But let's see if we can figure it out ourselves without the picture. So you would look at this, you identify the highest power right here. Let's go to the right first. Big positive number to the 5th power. Still a big positive number. Multiply that times -3. Now it's a negative number, so it goes down. Now give me a big negative number. We're going out the left side. Big negative number to the 5th power is negative. But then multiply it times -3, it's positive. So now that left side goes up. See that? Now, that's one way to do it. There's an easier way, not easier way, but a way that, if you like tables or notes or like cheat sheets or something, this is a way you don't have to think about anything, just it gives you the answer. But if you're taking calculus, it's much better to understand it the way that I just explained it. You're plugging in, you're thinking of a big number, what's happening to it, right? How is it behaving? So here's the idea. If the degree, the n, is even, then one of these two things is going to happen. Okay? Anytime you have an even-powered polynomial, even degree, you're either going to have this or you're going to have this. Up, or it's going to both sides up, both sides down. Now notice I have a question mark in the middle. The question mark is because in the middle, the n behavior has nothing to do with what's happening inside, right? We looked at this picture. All this squiggly shit in here, we have no idea about that. That's not what n behavior is about. N behavior is about the n behavior. So that's why I put question marks in here. If your degree is even, you're guaranteed both up, both down. The way to determine if it's both up or both down is by looking at what? What's a sub n? What is that? The leading coefficient, the number in front of it. If the number in front of it is positive, both sides go up. If the number in front of it is negative, both sides go down. Does that make sense how this chart works? So you find out, is your degree even or odd? Then once you do that, you look at your leading coefficient, move across and line them up and go into that little block, and that's the answer. So if you're an odd degree, you have two scenarios. Left down, right up, or left up, right down. And the way that's determined is with this leading coefficient again. So back up here, let's act like well, I'll give you a new one. Right there, I just changed it. What about this one? What's the left-hand behavior on this one? Tell me, left, up, or down? Left down? Left down? Right? Down. The way we did that, what's the degree? 6. 6 is an even number, so we're here, right? What's the leading coefficient? Negative. So leading coefficient negative and degree even, we're this. If I change it, this, now we're even and what? Positive. Both sides should go up. And you can see by the graph, that's what happened. Any questions? We're good? Okay. All right. Now, this is an important concept, so let's be ready. Everything up to this point, everything that we've looked at so far, remember the goal here today is to sketch these by hand, to sketch a polynomial function. Everything that we've talked about up to this point will allow us to do the first step of sketching a polynomial. We'll be able to determine the left and right hand behavior. Now, what we're going to look at are these x-intercepts. Remember, x-intercepts of a function, right? That's where the function hits the x-axis, right? There's some other words that you may hear. Instead of x-intercepts, you may hear somebody talk about the x-intercepts and refer to them as the roots of the function. Or you may hear them talk about what are called the zeros of the function. And before I actually do this, I want to just take a quick break to remind you of something we've done. And that way, when we start doing this, you'll be like, okay, we kind of done this already. If I gave you this on a test, on the last test you just had, that's a parabola. I'd ask you to sketch it, right? One of the steps was to find the x-intercepts. And to do that, you would set it equal to 0, wouldn't you? And then you would probably try and factor it. And once you factored it, what would you do with each of these factors? Set them equal to 0. When you set this equal to 0, you get what? X is 6. Okay? Over here, same process, you get X is what? -1. These are your roots. These are your zeros. These are your x-intercepts. Yes? Here's the important thing that's different that I want you to also think about here. If I tell you that 6, right? If I tell you that 6 is an x-intercept, doesn't that guarantee you that x minus 6 must be a factor of the function? So look at this function up here. Let's say that you did not break it down like this. Okay, you had not factored it. But I told you, hey, look, everyone, you see this right here? It has an x-intercept of 6. You would then, guaranteed, you would know that x minus 6 would be a factor of that function. Guaranteed. Same with this one. If x equals -1 is an x-intercept, then what's the factor? X plus 1, the opposite, right? So this is -1, this is plus 1 in here. I'm trying to get you to see the difference between the x-intercept and the factor. The x-intercept comes from the factor, but if I give you an x-intercept, you could go backwards to the factor, couldn't you? Okay, that's going to be an important concept today. So now let's go and look at this. All right, everywhere when you're talking about polynomials, all right, everywhere we have an x-intercept, the graph must do one of two things. One of two things. It's either going to cross through the x-axis, or it's going to touch or just bounce off the x-axis. So take a look at this function right here. Oh, that one's too boring. There's a parabola, right? Here it is right here, x squared plus 3x. Where does it cross the x-axis? Or what are the x-intercepts of this? 0 and -3. Okay, because 0's an x-intercept, that means that x is a factor. Why? That's right, x minus 0 is x. Exactly. I'm going to write this down over here. X equals 0, right, was an x-intercept, which meant that x minus 0 is a factor. What's x minus 0? X. So you can see that, see how x is a factor here? We could tell that from this picture. Where's the other x-intercept? -3, which means that what is a factor? X plus 3. And you see that's the other factor right here. So if you had started with this and it factored out, this would be it, obviously, because that would just be a GCF problem. But you can see that, I'm trying to get you to see two things here. If you start with the picture, you can almost come up with the function, can't you? Kind of? Kind of. We will do that, but, or if I start with the function, I can obviously somehow come up with the picture. I mean, it's got to go both ways. So would you say that in both of these x-intercepts, I cross through the x-axis? And I said it's either going to cross or it's going to touch, right? Let me show you the same idea here. Pay attention to this right here. I'm going to change something. Change it to a cubic, and I'm going to put in, okay, what are the x-intercepts of this one? 0 and -3. Same two x-intercepts, aren't they? But the function is different, isn't it? What is it? What's the degree of this polynomial? 3. If you could factor this, look at what the factors are. Now, I'm not showing you how you could factor this, but what does this x come from? That x right there corresponds to that 0 right there, right? X being 0 gave us this factor, didn't it? And what did I do here? Cross or touch the x-axis? I crossed through, didn't I? What's happening here? Am I actually touching the x-axis? Yes, I am just touching it though, right? So I do have an x-intercept of -3, don't I? Yes? So that should create a factor of x plus 3, shouldn't it? Which I have, but do you see the difference? What's the difference between this one and the one before? It's squared. And because it's squared, that's what creates the touching instead of the crossing through. If you take the squared off of this, oh, that's not what I want to do. There. If I take the squared off of this, right, it gave me a parabola, crossing through it both. But if I come in here and I take this factor right here and I square it, that's going to create the touching that I want, that corresponds to this graph. I hope that makes sense. Let me try something else. What if I change this right here, this x right here, to an x squared? What's going to happen? It's going to be a fourth polynomial, right? 4, which means both sides should do what? Go up, okay? So it's going to be a 4th degree polynomial. Both sides should go up. What's going to happen at that 0? Am I going to cross through? I'm going to touch instead of crossing. So let's see. I've got to change it to a 4th degree. And let me change that to a squared. There it is, right there. Do you see now? I have the same two x-intercepts I've had from the beginning, but now I'm touching at both of these. So let me see if this now makes sense to you. How can we determine the crossing or touching behavior of a polynomial? How can we tell? To do this, we will need to be able to factor the polynomial. And that is going to suck for us at some point in time. Once we do that, once we have factored it, we inspect the power of each factor. So what I mean is we this is it not factored, right? This is it factored. Once we have factored it, we inspect the power on each of the factors. So what's the power on this factor? 2. What's the power on this factor? 2. If the power is odd, we're guaranteed to cross through. If the power is even, we will touch or bounce off the x-intercept. Let's see if we can put this together, all right? We just have to get practice. Here are the set of steps. Did I tell y'all that did I tell y'all I used to do triathlons? No? Yeah. So I'm on a mission right now, and I want y'all to hold me to it. I'll make you a deal. Okay? I don't know if this is good for you or bad for you. I have a target as far as I've been doing biking again, okay, which is one of my favorite pastimes. And I have a goal of getting down to like a competing weight again for my triathlons. So my goal is by the end of this semester to have lost 25 pounds. Okay? If I don't reach my goal, okay, everyone will get a 5-point bonus on the final. Okay? No, I don't want food. Okay? I think it's more realistic that way. Okay? If I don't reach it. So that'll hold me to it because I don't want to just give everyone 5 points just for nothing. So, all right, sound fair? Yes. You're just going to have to trust me. I'm logging it every day. I mean, I'm going to reach it. I'm going to reach it. So, you know. Well, I'm already down 8 because the first 8 go easy. Those are all water and everything, so. Huh? Yes, it's from where I started, so, yeah. So I'm right now I'm still 15. I'm like 15, 16 from where I need to be. So, we'll see what happens. That's my goal for the end of the semester. We'll see if I can reach it. It's going to be tough. Why am I talking about this? Yeah, because I'm trying. Well, but I'm trying. I understand that. I don't need health advice right now. I've dropped 40 pounds before, when I know how my body works, so I'm good. Don't worry about it. If you make it, that means you're happy. You're going to give us 5 points anyway. I might, man. Who knows? Who knows? Who knows? All right, we need some steps. Y'all just gotta hope I don't like hurt myself. You know, like walking down the stairs. I'm getting old, so you know, I blow a knee out or something. I guess that would be good for you, right? Yeah, y'all don't mess with me. Don't be like tripping me or. Maybe I should change it. Yeah. Okay, look, these are the steps. Okay, you have a procedure. And this looks pretty nasty. You'll be allowed to have this on the test. All right? You can have the procedure. All right? But I want you to follow it. So, all right, first of all, this should look familiar. Step A. Make sure you're looking at a polynomial. That was step A of the quadratics, wasn't it? Make sure you're looking at a quadratic. So we want to make sure we have a polynomial. Then we want to determine the left and right-hand behavior. You can use that table that I gave you earlier, right? The next thing is to find the x-intercepts. That may, like I said, require a significant amount of work. We will spend the entire next class looking at factoring in a way that you probably have not factored before. Because there's some things we cannot factor right now. Then we'll find the y-intercept. We'll determine the multiplicities of the zeros. What does that mean? Multiplicities, what was that? That was multiplicities. That was where it's going to touch and cross, okay? So we'll determine that. We'll plot the x-intercepts and the y-intercept. We'll sketch the left and right behavior. We'll connect the dots. We're going to go back to like kindergarten. We're going to connect the dots with a smooth continuous curve, being sure to follow the crossing and touching characteristics determined from step E. Yes? Y-intercept's always going to be the same. Yep. All right, and I have a bunch of examples. So our first example, all right, step A. Is this a polynomial? Well, it doesn't have the format of a polynomial, right? Isn't a polynomial like something plus something plus something plus something, right? All added together or subtracted? If we multiply this out, would it be a polynomial? Yes. But we don't have to do it, all right? As long as we agree that it would be. Now, I think just because it's the first example, I will just put up here what this would be. So what I did there is I took this right here and I squared it. Remember when you square it, you put them side by side and you FOIL or expand, right? And then once you do that, you would have to come through with the x. X cubed plus 4x squared plus 4x. So what we have here, boxed up here on the right side, is the polynomial in expanded form. Here's the polynomial in what form do you think? This is factored form, right? So I gave you the polynomial in factored form. Step A, is it a polynomial? Yes. Step B, determine the left and right hand behavior. Now the way to do that is to go look at this, right? But I said we don't want to multiply it out, do we? Not every time. So let me show you a shortcut to get to x cubed, because that's the only thing that matters, right? All I do is I look back over here. I say, look, I have x, right? What's the power on that x? 1. Then in here I have x, but what's the power on that x? If I FOIL that out, I would get a 2, right? So this is going to be like an x times and then an x squared, which would be x cubed, which matches up with this. So you don't have to go and actually multiply the whole damn thing out as long as you keep track of all the powers of the x's. What does x cubed do? How does it behave, left and right hand behavior? Do y'all like this? Yes? So what's the degree? X cubed? X cubed, the degree is 3, it's odd. And it's x cubed, so what's the number in front of that? 1, that's positive, so it would look like this. It's going to go down on the left, up on the right. Yes? Pardon? How did I get the odd? Okay, let me bring up my notes again. The odd power, right? The degree of this is odd. The leading coefficient, the number in front of it, was a 1. Did I answer your question? No? Yes? So this leading coefficient, I'm going to say LC, is positive, and this degree right here is odd. Yes? So what's the left and right hand behavior? How do I want you to write it on the test? Just draw that little thing like this. If you do that, I'm a happy man right there. All right? Right here is the left and right hand behavior. That's part B, yes. What is part C? Determine the x-intercepts. How do we determine x-intercepts of any function? Set the function equal to 0, right? But this function is already written as a factored form, which is absolutely fantastic for me, right? Because if I need to set this to 0, all I have to do is set each factor to 0. So let's set, go ahead.
When we find the x-intercept, we only take the first equation of the expense that has the
You could do this one, but your first step, if you were trying to solve this equal to 0, the first step would be factor. So these first problems I'm giving you, if you look at the problems that we have here on the notes, look at numbers 1, 2, 3, 4 are all factored already for you. Numbers 5 and 6 do not come factored. So we will have to factor it later. Yes? Question? Taking out, what do you mean? That's factoring. That's factoring, yes. Yep. Let us get to the other examples and you'll see. Okay? All right, so we've got it factored. Set each factor to 0. So I'm going to set x to 0. I'm going to set x plus 2 to 0. The fact that it's squared does not mean I have to do this twice, right? I only have one factor. So I set x to 0. The other one I set x plus 2 to 0. My two answers are what? 0 and negative 2. Ooh. Okay, these are my x-intercepts, right? I could also call these my zeros or my roots, okay? So those are my roots. D, y-intercept. Plug 0 into the function, right? That's how we always find the y-intercept of anything. Let me write y-intercept down here. Y-intercept, you always plug 0 into the function. So that would be 0, 0 plus 2 squared. But that 0 in front is going to kill everything off, 0. So this is a point, right? 0, 0. You could just say y is 0, and that would be fine. We have completed part D. Part E, multiplicities. This is the most important part of the entire problem, all right? What are the multiplicities? So this is part E. So first, let's write down what our two roots are. 0 and negative 2, right? Those are our two roots. I want to know if I touch or I bounce there. So what I have to be able to do is go back up and see where did x equals 0 come from? What factor did it come from? Well, this came from this came from this, right? What is the power on that factor? There is a 1 up here, isn't it? That power 1 will dictate now the multiplicity of this. 1 is an odd number. What happens if you have an odd number? You're going to cross through the x-axis. So this is odd, so therefore you're going to cross through here. Make sense? What about the negative 2? Well, negative 2 came from the factor x plus 2. X plus 2, the power on it was 2. That's even, right? So that 2 tells you that this one is going to touch. Check it out. See, I got this too. That's what I should be drinking right now. I just need a little caffeine. What's that? What is? Oh, yeah. Thanks, man. That's a nice thought. F. F. What's F? Plot the x-intercepts and the y-intercepts. Okay, critical point. Any questions on part E? All right. At the factored form. Now, fortunately, it was factored when we got it. It's not going to be on the test. On the test, it's going to be ugly. You'll have to factor it, and that's what you'll refer to for multiplicities. Okay? Okay, so does it say that in the notes for multiplicities? Let me see. Yeah, it says, to do this, we will need to be able to factor the polynomial. Once we do that, we inspect the power of each factor. So it does say it in the notes, reminds you, I guess. Okay, part F, it's time to draw a picture, okay? These pictures of polynomials do not have to be perfect, all right? They don't have to be perfect. So let's just draw a quick x, y axes. What are my x-intercepts? 0 and -2. What was my y-intercept? 0, 0. So that x-intercept is also my y-intercept. So I've got all the information plotted. This is part F. Part G, we actually do on the same picture, all right? Part G, I want to sketch the left and right-hand behavior. All right. Another critical juncture of this problem. What was the left behavior? Must go down forever. So what I'm saying is this. I know that these 2 points live on my graph, don't they? I know from this point, I cannot go up and then come back down. Why not? Because if I go up, I've got to come back down and cross through the x-axis, which means I should have another x-intercept there, right? See, left-hand behavior is down, right? Down. So I've got to eventually come down. Since I cannot go up and then back down, I just, from this point, have to go down. So I'm going to very lightly, because I might need to erase this, I'm just going to kind of tell myself, it's going to just kind of go like this. Very lightly. I know that that goes down. What does the right side do? It goes up. So I'm going to go to this point. There's nothing to the right of it, right? I know that I must go up from here. So I'm going to very, very lightly just kind of say it does that. But now we use the multiplicities, right? We sketch the left and right. Now we're on part H, which is also on this graph. Part H, what do? Connect the dots with a smooth continuous curve, being sure to follow the crossing and touching characteristics. So what was I supposed to do at -2? Touch or cross? Cross, touch, cross, touch. At -2, I was supposed to touch. Now, I used a different word than touch than the book uses. The book uses touch. I like to use bounce. Like a wall, you bounce off of it, okay? Crossing means you go through it, right? So I'm supposed to, when I draw this, I'm supposed to just touch here, and then I'm supposed to cross here. So do you see it's going to look like this? See, now I'm going to come in here with a nice graph. I'll erase that black stuff. I'm just going to touch there. Do you agree that touches? Notice I also drew it smooth and curved. I didn't draw a corner, right, a V, because then it's not a polynomial. So I drew this nice little curve. And now what do I need to do? Connect the dots. I've got to go back up to this, don't I? Now, can I do this? Why not? More than one y. Okay, can I do this? Why not? Is it a function? Fails the vertical line test, right? So I know that I must come down, and then I must get back up to this point, right? Then once I get to that point, I must cross through and continue up. Now I'm going to erase that stuff that I really lightly sketched in there. And I'm going to say that's my graph. Yes? Great question, which I'm going to defer to the notes. At the very bottom of this, read that note. We will not be able to determine the local maximums and minimums in our sketch, so our answers may vary. In other words, when we look at this, I don't really know how low that goes, all right? So you may draw it, and your answer may be this. Yours may look like this. That's no good. Okay? That would be correct. Our answers are going to vary. What they will all have in common are these characteristics. Look at the blue one versus the red one. What are the x-intercepts for the blue and red? Same. What happens at -2? They both touch. Touch, bounce. Okay. What happens at 0? Cross. Where is the blue function negative? That means below the x-axis. Over here, right? Same as the red, right? Also below the x-axis here, which is the same as the red. Yes? Where are both functions above the x-axis? Positive. Over here, right? So they both have those characteristics in common. The x-intercepts match, the bouncing and crossing matches, where the function is above and below the x-axis matches. How high, how low? Calculus 1. That's what you do in Cal 1. You figure out how low do you go, all right, here, right? That's what you do. This would also have been correct as an answer. Right? That would have worked. That's the same graph coming up here. This is going down forever. This is bouncing off. It's going through. It's crossing through. It's going up. All three of those are good. That's why I said you don't need to draw a graph like with the quadratic, right? We had to find the vertex, the x-intercepts, and draw a nice. This is different. We just want general basic graph picture of what's happening. Okay, let's try and do another example. We're done with that one. Okay, how about this? Number 2, f of x equals x minus 1 squared, x plus 3 squared. Part A. I'm going to move quick through this. Is it a polynomial? Yeah, you would have to multiply it all out, wouldn't you? But it is a polynomial. How about left and right-hand behavior? This is x to the second power, right? This is x to the second power again, which means that this looks very much like x to the fourth power, which means I go up on the left, don't know in the middle, up on the right. That's my left and right-hand behavior. Part C. What's C? X-intercepts, right? Set the function equal to 0. It's already factored. I love it, right? Well, love's a strong word. I'm happy, right? Set each of those factors equal to 0. You get two solutions, 1 and -3. I didn't show setting them each equal to 0. Remember, when you set factors to 0, though, this won't matter when you set it equal to 0, right? The fact that that's squared, ignore it. Okay, part D. That's plugging 0 into the function, isn't it? Y-intercept, f of 0. So be careful plugging 0 in here. 0 minus 1 squared, 0 plus 3 squared. What does that give you? 1 times 9, which is 9. So your y-intercept is 0, 9. So just plug 0 in for x here, 0 in for x here. You're squaring -1. -1 squared is 1. You're getting 0 plus 3 is 3. Squared is 9. 1 times 9 is 9. Part E. What are the multiplicities? At x equals 0 and x equals -3. Even or odd? They're both even, right? They're both even on these factors. At 1, that comes from this factor, it was even. At -3, it was this factor, that's even also. So it's going to bounce off both, right? Yes. I'm not sure what you mean by positive polynomial, but yes, on both ends, yes. Even. Even, so it's going to what? Bounce? Do y'all like bounce or touch? You like bounce? I can't even spell bounce. Or touch. All right. Part F. Draw a picture. Questions at all? All right, so here we go. Draw a picture. I'm going to do it all on this one page. I do have a y-intercept up at 9. So there's a y-intercept. I have an x-intercept at 1 and at -3. I do want to stress here real quick that when you're graphing things, remember that your x-axis and y-axis, the scale doesn't have to be the same. So like if you're saying that much is 1 unit on the x-axis, you do not have to say that much is 1 on the y-axis. You can change it. You just can't say that, you know, this is 1 and then this direction that's like -5. On the same axis, you have to keep the distances proportional. No, not proportional. The same. All right. What's next? So what part of it? Left-right behavior. So what's my left side supposed to do? Up. Right side? Up also? From these two endpoints, right? From the two endpoints. And then I'm supposed to now draw this, and I'm supposed to touch or bounce off of these. So it's going to come down like this, right? Bounce up. Now, how high up do I go? I don't really know, but I do know I need to go through that point, don't I? And then come back down to this. And then when I get here, bounce off again. How I do that is kind of up to me. So here's my rendition of this polynomial. Oh, I struggled there with that bouncing off this one, but that's supposed to bounce. Is that all right? So, and then put little arrows at the edges of these to show that it goes up, you know. So I come down, I bounce, I go up, I come through the y-intercept, I bounce off, and I go back up. Yes? Straight? Yeah, you could have done this. Absolutely. You, like, you know, do something like this. I don't know. Like, make that your highest point. As long as you bounce off this one. Yes, that would be fine too. The only problem with that is you don't know if that's your highest point, really. You don't know. I can tell you. Is it wrong? No, it wouldn't be wrong. Not at all. No, I won't take that. Won't take off for that. Okay, so look, maybe you'll be able to see how I built this program. All right, the one we just did. What was the degree of the polynomial we just did? 4th degree, right? I had 1 0. What was one of our zeros? Let's start -3, right? But it was -3 squared, wasn't it? So I put -3 twice. Now the other 2 zeros, what, that was 1? So it was 1, but it was squared, so I do 2 of them. And if I do that, here's my picture. I think that's good enough. It's obvious from this picture that that 9, that y-intercept, was not the highest point, but again, I wouldn't take off for that. We can't tell that stuff. But doesn't that look a lot like what we have? Yes? Okay, good. There's about 13 minutes left. I have enough time to maybe do another one. I'm going to do one that's not factored. So let's do, which one do you want here? 5 or 6? 6? Okay. I didn't really make them in order of difficulty. 6, so we have the function f of x equals 2x to the 4th plus 10x cubed minus 8x squared minus 40x. So I hope that you can see some appreciation for what we've actually done today. Because I mean, just imagine we walk in class, beginning of class, I'm like, okay, we're going to sketch that today. You know, you'd be like, what? You know, that looks pretty crazy, right? The key to the whole problem is, can we factor that? That's what the key is going to be. So part A, it is a polynomial. Yes, it is. Part B, what's our degree? 4, that's even, right? So n is even. Leading coefficient is 2, it's positive. So off the table, up, up, right? Should go up on both ends. Step C, the x-intercepts. So we set the function equal to 0. And here's where the issues start to happen. Yes, we have to factor this. That's exactly what we have to do. Oh, in the very beginning of the problem? You're going to need to do it eventually. If you want to do it in the beginning, you can. So let's go through this. Right now, there should be certain things that you can and cannot factor in this class. Right? We assume that coming in. Let's see if we can factor this. First technique of factoring anything is GCF. Do you have a greatest common factor? X and 2. I can pull a 2x out. I'll be left with x cubed plus 5x squared minus 4x minus 20. Everybody agree with that? Common factor of 2x. Now what's in parentheses there, hopefully will factor. So you look at it, you say, what have I learned in the past about factoring? Well, how do you factor something, how do you try to factor something that has 1, 2, 3, 4 terms in it? Grouping. Okay, so this is where you might want to make stars on the side of your page, like he said grouping and I have no frickin' idea what he's talking about, all right? And then go get help on that. Grouping, you split this thing, the 4 terms, right in half, and you look at the first 2 terms and you try and pull something out of this. So watch the way I write this. This is equal to 2x. What factors out of these 2? X squared. What would be left right here if I factored x squared out of this one? X plus 5. Now, if you want grouping to work, the other one is going to have to factor also, and you're going to have an x plus 5 left over here. Negative 4 comes out of both of these, right? So I put a negative 4 right here, then in parentheses, x plus 5. That is me doing the grouping. I'm doing grouping inside this big red parenthesis. I'm doing the grouping in there. Pulled x squared out of that one, pulled negative 4 out of that. Now, what does grouping allow you to do now? You put, okay, so let me see if you're comfortable with this step. Okay, whoa, 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 that's weird. This right here becomes this. Again, make a star, come see me in my office, go to the tutoring lab, say, hey, just can you explain the grouping here, right? What essentially you're doing is you're taking this x plus 5 here, and x plus 5, and you're pulling it out. And when you factor this and this out, it's right here, and what's left is the x squared and the minus 4. And now we have still equal to 0. Notice anything else? That's a difference of squares. 2x, x plus 5, x plus 2, x minus 2 equals 0. Yes, but what you would have lost was the being able to identify the multiplicity. So we need to be comfortable doing difference of squares there. What if grouping didn't work? Come to class on Thursday, and I'll show you exactly what we're going to do. Yep. That's what we want to be able to do on Thursday, is factor something that grouping fails on. Stay tuned. All right, what's the next? What are our x-intercepts here? You said each of these factors equal to 0. 0, -5, -2, and 2. So we have 4 x-intercepts. That was just step C. Step D, the y-intercept. Plug 0 into the function. This should be pretty easy to plug 0 into this function, because before we factored it, it was really easy to see what would happen if we plug 0 in here, right? We just kill everything off. So we just get 0. Part E, multiplicities. What is the power on the part that gave us the 0? Well, that tracks back up to the 2x. The power on that is 1, right? Odd. So we have an odd power on that x right there. So it's going to what? Cross. Look at all of them. All the factors are odd, aren't they? They're all 1, 1, 1. So that means every x-intercept we are going to cross. So I'm just going to put here cross at all x-intercepts. Worked out that way. Make sense? And we're ready. See how quickly we can graph this. X-intercepts were 2, -2. I'm just going off my memory here. 2, -2, -5, and 0. Y-intercept is already there. What comes next? Left-right behavior comes next, right? What if you get the left-right behavior wrong? The rest of your graph's wrong. The left and right has to be correct. So what was our left behavior, right? It was up, up? Okay, so I've got to go up, up. So I've got up over here and up over here like this. I've got to cross through each of them. So I'm starting to imagine this. I'm just, with my pencil, I'm tracing this out. I'm going to go through, I'm going to cross through, got to come back up to this one, cross through, got to come back down to this one, cross through, got to come back up to this one, cross through. That's it. So there it is. We didn't quite get as far as I wanted to go. We still have a couple of things. Oh, come on, hold on. 3 minutes? 3 minutes? 3 minutes? I think you can do it. Just tell me real quick about this one. Instead of starting with the function and doing the graph, what if I give you this graph? Can you tell me what the function might look like? What does this mean right here? X plus 1. X plus 1 is a factor, right? But what else about it? What are we doing there? It's bouncing, so it's got to be an even power. So you mean to tell me it looks like this? It's got like an x plus 1 and then a squared? Okay, where else do we have an x-intercept? That right there is 2, so x minus 2 should be a factor. Should it be squared or not? No, because I crossed through. So x, but it could be cubed, right? Okay, hold on, x minus 2. It could be cubed, and we don't know that. That's why it says construct a polynomial that might have this graph. This could be to the 4th, yes. But let's go with the lowest one, okay? So that makes sense. Now, Okay, y'all with me on that? Okay, there's one more piece of information they give us. They give us a y-intercept, don't they? Right now, if I plug 0 into this, it needs to spit out what? -2? What would happen? 0 in here, that give me 1. 0 in here would give me -2, right? That would work, wouldn't it? But that's not an efficient way of doing it. So here's what we do. We say that our function is that. I still have 2 minutes. I'm going to write this up here so that it's in your notes. We said that we had come up with a function that looked like this. F of x is, I think we all agreed on x plus 1 squared and then x minus 2 to the first power. We all agreed on that. But what could happen is that there could be a number out in front of all of it, like in front of the x to the third power, right? Because this is x cubed eventually, right? X squared and x, that's like a third degree polynomial, right? There could be some number out there. It could be like 4x cubed or -2x cubed. So what we do is we always put an a here, and then we use the y-intercept. The y-intercept means, what was my y-intercept? 0, -2. That means when I plug in 0 for x, what should come out of the function? -2. So what I want you to do is take this equation right here, make the left side -2, leave a, whatever a is, and plug 0 in for x. And if you do that, you can solve this for a. It's going to turn out to be 1, but it could, in your homework, not turn out to be 1. All right, so this is a. This was 1, right? 1 squared was 1, so times 1. This is -2. Now divide both sides by -2, you get a is 1. So your answer would just be this, okay? That would be a function that would model that graph. No, because like let's say this side right here was -4, right? You plug in 0, you get -4 out. Then you would have divided by -2, a would have been 2. And so your answer would have been this with a 2 in front. We'll address that more. Do as much of your homework as you can comfortably. I will give you one piece of advice. When you get to the point where they ask you to sketch it, they say refer to the 6 steps in the book. Throw that out the window. Just do what I did in class, all right? Unfortunately, my homework solutions, when I did them, I followed the book's method. And after doing it all, I was like, why? That's not the way I'm going to teach it. I don't like the way the book does it. So just see if you can get the same graph that I get. All right, everyone. Have a great day.